Hi, okay. Good morning, everyone. Thank you for coming again.
Sorry, third lecture. Yeah.
Third lecture, yes, yes. I was going to confirm that this was indeed the third lecture, just that I got it right. Welcome to the third lecture on a primer on the signature method of machine learning. The first thing that I wanted to do today is just briefly recap what we did in the first two lectures. So in the very first lecture, I introduced something called the signature of a path. This was essentially the collection of iterated integrals of this path, and we were essentially always working with piecewise smooth or bounded variation paths. So this I denoted by the letter mathcal p. And then we began studying some of its basic properties. So we in the first lecture, we looked at some of its geometric properties, and then primarily in the second lecture, we looked at its algebraic properties. So I've included some of the slides from the previous lecture here. I'll briefly recap with these slides the algebraic properties that we looked at. So we began by looking at the shuffle product, and the shuffle product essentially was a generalization of the multiplication rule for polynomials, the very, very familiar multiplication rule for polynomials. And so this justified essentially the fact that the signature is an analog of polynomials for paths, in fact, for unparameterized paths, because the signature is parameterization invariant. Okay, so the main kind of content there was this theorem of Chen and Rhi, that if we multiplied two signature terms, so we took two words I and J, we multiplied their signature, their respective signature terms, this could be expressed as a sum of other signature terms. And the words in the sum range over all shuffles between the words I and J. Okay, so this had a few nice consequences, like the fact that the signature terms form an algebra, and this kind of motivated the fact that there should be a positive solution to the moment problem for signatures. So kind of expectations of signatures can help to determine the laws of stochastic processes. So then the next basic algebraic property that we covered was Chen's relation. And the motivation for this algebraic property was about how to compute the signature effectively. So it was kind of an alternative to directly integrating these curves and directly computing these iterated integrals, either analytically or numerically. I see that there's, okay. So Chen's relation, when written explicitly in terms of words, is this this object down here. So you deconcatenate all of, so for every word I1 up until ik, you split it up into all of its two subwords. So from I1 up until im, and then im plus 1 up until ik, and then you evaluate the signature over the two respective subintervals. So this allows you, so if you know the signature over two subintervals, this allows you to compute the signature over the whole interval. Okay, so right, and then I kind of tried to formulate this in a slightly more algebraic framework, to write Chen's relation in a slightly more compact way. So in order to do this, I introduced these indeterminants. So I1 up until ID, and these determinants are non-commuting. So when I multiply E1 with E2, this is not the same as E2 and E1. Okay, and then so the signature can be naturally viewed as an element of this big vector space of formal series in D non-commuting determinants. And then Chen's relation takes on quite a nice form, which is that you look at the signature over the interval AB, and you multiply this by the signature in the interval BC, and you obtain the signature over the whole interval. Okay, so then we saw some basic examples of this. So for piecewise linear paths, this gave a very nice way of computing the signature. So we know that for a linear path, the signature is equal to a natural exponential of the increment of the path. So if we have a linear path xt is equal to tx, then the signature is equal to the exponential of x when taken inside this algebra. And so the punchline here was that this was a much simpler computation tool than just integrating directly. Okay, so for in general for a piecewise linear path, it follows then from Chen's relation and this exercise that this is the formula for the signature. Okay, so then we talked a little bit about another form of Chen's relation in terms of concatenated paths, a little bit more algebra, which I'm not going to. This slide is somehow I don't think it's particularly important for understanding of this computation method, okay. Okay, then we looked at what happens at the time reversal. So signatures kind of get inverted if you reverse time. So if you multiply a signature by the time reversal of the path, this gives you the identity. So this is the element of TRD, which just has 1 in the kind of the 0th level and 0 everywhere else. So this is the identity under this concatenation product. Okay, so, and I think that this is essentially where I left off. So a consequence of this was that we could now see a natural family of paths for which the signature is trivial, for which the signature is the identity. These were tree-like paths. Okay, so with this quick recap, I'm going to actually backtrack a little bit and do something that I should have done maybe when introducing the space of formal series. So I'm going to do some hands-on computation in this space T of RD, so in this space. So I'm going to show explicitly how the basic operations operate in the space, so that at least now you can kind of, so if you didn't catch all of these kind of how these tensor products work, you can now go back and hopefully after these hands-on computations, you can see how these computations look like for the signature. Okay, so the most basic thing, so I mentioned that it was a vector space. So T of RD is a vector space. So how does addition of its elements and multiplication by scalar elements look like? Well, it's exactly what you expect it to be. I mentioned that these guys were kind of the basis vectors, if you like, or like there's some form of vectors. So if I add together two power series like this, so I add together power series with coefficients xi and coefficients yi, then for each one of these basis vectors, the coefficients just get added together. So it's just like this. So it's exactly what you expect it to be. So this is how addition works. And scalar multiplication works in exactly the same way. If I just multiply a power series by some constant c, then the constant comes in front of here. So it comes inside the sum. Okay, so this is the elementary addition and scalar multiplication that I completely brushed over before. Okay, so then maybe a little bit more interesting is how does this product, this sort of tensor or concatenation product work? So suppose that we're given two series, x and y, and x takes on this form, y takes on this form. And I've written down the first two terms of each one of these guys on the right. So each one of these series always has a 0th level term. So this is just a real number. So this is, so x empty set, this is the coefficient of the empty word. This is always just a real number. So remember for the signature, this would be 1. So if x was a signature, this coefficient x empty set would always just be 1. And then each one of these xi is of course a real number as well, but then the ei is a vector. And then you continue this up to infinity. And then of course the same thing here. Okay. Okay, so then I defined previously how this tensor product worked for the monomial. So for these basis vectors EI and EI, EJ, but I didn't really spell out how it worked for when I put this into series together. So in short, it works by extending the definition for the two basis vectors by linearity and multiplicativity, or associativity rather. So so the way that so if I were to multiply explicitly these two series together, x and y, the answer that I would get is the following big long series. So I multiply their empty words together, and this here gives me a new real number. This is the new 0th level. And then for each vector EI, I would look at all the ways that I can combine the coefficients of x and y in order to form the letter I. So the empty set and I together form I, and then the empty set I here and the empty set, and then the letter I and the empty set also form I. So this is the two ways of forming I from the coordinates of x and y. And then for the second level, I would do the same. So for every word ij, I would look at all the ways of splitting up this word into two subwords, and then I would multiply the respective coefficients of x and y together. So the answer would be given here. And so in general, there's an equals missing. So in general, this is equal to, okay, we sum over all lengths from k is equal to 0 to infinity. We look at all words of length k, and then the coefficient of this basis vector EI1 up until EIK is going to be given by essentially splitting up this word into two subwords and then kind of multiplying the two respective coordinates of x and y together, and then taking the sum over all these splittings. Okay, so this will be the new coefficient of this word. Yeah, so this is how multiplication works in this for general series. So I sort of ignored this explicit computation in the previous lecture, but it might have been good to give it here, kind of to demystify how this algebra T of RD works. Okay, so if you're writing a computer package, this is exactly the program. This is the algorithm that you would use. So you would multiply these vectors together according to this formula. Okay, so then I mentioned at the end of the last lecture that I would speak about the log signature, which is a more compact way of representing the signature. And so now I would like to actually, as a prelude to that, I want to point out quite an important aspect of these series. So a very useful remark is that if we take a series whose 0th level is 0, so suppose that we have a series like this. Notice that k here begins from 1. So the coefficient of the empty word is 0. So in other words, we have this equality. Okay. So then we have the following rules for how to compute the powers of x, the powers inside this tensor series. So if we multiply x by itself, so x to the power 2 is just x multiplied by itself. Then what we notice is that there's no terms in here of the form, so no terms form CIEI. So there's no 0th level. This is because if we go back to kind of say this product for the x and the y, we see that the only terms that appear for EI here are that they have to contain an empty set. So either the empty set from X or the empty set from Y. But I imposed that, so here Y is equal to X, and I imposed that this was equal to 0. So there's no first order term when I look at the second power of X because of this condition. And then likewise, if I look at higher order powers, so if I look at the third power of X, I see that the lowest order term is actually going to be a triple product like this for the same reason. So because the lower order terms would all have to contain some coefficient, they would all contain at least one coefficient with the empty set. Okay, and then of course there are kind of these higher order terms for words of length 3 and bigger or 4 and bigger respectively. Okay, so generally if I look at the nth power of X, then the lowest order terms that appear are of length n here. Okay, so this generalizes in this way, and then a bunch of other terms of which are indexed by words of length n+1 and more. Okay, so this is a helpful remark, and it leads to perhaps a slightly surprising way that that this tensor algebra, this space of formal series behaves, which is the following. So consider now any real numbers, a1, a2, and so on and so forth. So I'm going to consider any sequence of real numbers. And I'm going to consider the following power series. So this one, this here. It's probably a familiar fact that if X was equal to R, and I replaced this this kind of fancy times with just a normal power. So I just replaced it with this an to the xn. So if X was equal to a real number, then this has no reason to converge. So we've all seen kind of diverging series. So unless X is say 0, this in general doesn't make any sense. But perhaps surprisingly, for special X inside this space of formal series, this power series makes perfect sense. So notice that our X, so recall that the X that we were considering had X empty set equal to 0. So X was essentially equal to sum of words of length bigger than or equal to I of xi times ei. So this was maybe a compact way to write this. So x to the n, we just saw in the previous slide that x to the n always takes values in kind of the grade, which is level n and more. So of degree n and higher. So what this means is that if I look at the kth level, so if I look at, if I try to compute this big expansion, and I look at all the words of length k, so I look at kind of this the space spanned by these words of length k, then the only elements of this power series that contribute to this level will come from the first n elements of the series. Because once n goes above k, this whole, any contribution to that comes from this power series will be at level k+1 and more. So actually, at every level k, there's only finitely many terms from the sum that contribute to that level. So if I was to compute the coefficient of a word of length k, I would only need to look at this sum here. I would never need to look at n bigger than k+1, bigger than k. Okay, so a consequence of this is that no matter how I choose these real numbers, AI, this power series always makes sense as an element of this tensor series, so for formal series. So what this means is that there's no issues of convergence when I look at formal power series like this. It's because of this kind of the fact that when I multiply elements together, provided that there's no 0th level, I kind of always increase the level of inside of these products. So it's kind of it's using what's called the graded structure of these formal series. Okay, so with this prelude, I now want to introduce the log signature. So hopefully this doesn't hopefully this will demystify some of the things that appear on the next slide. So recall that the shuffle product identity implied that the signature terms they're not algebraically independent. So if we wanted an independent set of features, so perhaps if we were to find a set of features that were algebraically independent, this should be a more compact way of representing essentially the same information. So if we were using some nonlinear machine learning method, then this the fact that it's a nonlinear method, it should still pick up the other terms of the signature that were lost through this reducing to a smaller subset. So this independent set of features is called the log signature, and the way that it's defined. So let's consider a path over AB. Then its log signature is just denoted by log of Sx, and it's an element of this tensor series. And the way that it's defined is well through a power series. So we define it according to this formula. So this is where that prelude that I had now starts to kick in, because we notice that this term is exactly so this is our new this is the X that I was looking at before. So recall that the terms of the signature are like S of X is equal to 1. So this is the coefficient of the empty set plus all the words of length I bigger than or equal to 1, S of xi times ei. And so if I take 1 and I subtract the signature from that, this so 1 minus S of x, this is just equal to minus times this. This is the same thing before. This is exactly of the form that I was looking at on the previous slide. So this is the x with whose coefficient for the empty word is 0. And then so this x I raise to the power n, and I multiply by some coefficients an. By some coefficients an. So these are the coefficients here. These are the an from before. Okay, so why is this a natural definition for the logarithm? Well, this is because if you take a look at Taylor's theorem for the logarithm, just the usual logarithm that we're familiar with, then this is exactly what you get. So this is the Taylor expansion for log of x, with kind of the center point being equal to 1. And so again, kind of a surprising fact is that the classical, if you were trying to compute the classical logarithm on the real line using its power series, it has a strictly finite radius of convergence. So if you look at elements of x which are too big, then this series will diverge, because it essentially looks like a harmonic series, like an oscillating harmonic series, with some geometric weighting. So if this geometric weighting is too big, then this is going to diverge. But for us, there's no issue here because of this graded structure for the space of formal series T of RD. Okay, so there's no issues in terms of this is a perfectly well-defined object. So I haven't brushed anything under the rug. Okay. So this is the definition of the log signature. So then I want to present a theorem that shows something quite important about this log signature. This log signature lives in a very natural vector space. Maybe on the on the next slide I give a slightly different way of writing it. So we're going to equip the space of formal series with a Lie bracket. So a Lie bracket is an anti-symmetric product, often denoted. So the product between x and y is denoted with these square brackets, which satisfies. So it's anti-symmetric, satisfies Jacobi identity. For us, we can just give an explicit definition, and it's so I actually don't care what a kind of axiomatically bracket is. So for us, the bracket between x and y is just this kind of anti-symmetric product between x and y. So we take x times y and we subtract y minus x, y times x. Okay, then we're going to denote by this curly L, essentially. So it's formally it's the smallest Lie algebra that inside of this space of formal series, which is generated by this by the kind of the first level of this formal series, and then we kind of complete it by allowing series rather than just finite sequences. So actually, the smallest Lie algebra would only contain finite sums, but we allow it to contain infinite sums. So for formal series rather than just polynomials. Essentially, very concretely, the space L contains all terms that can be generated by, so kind of all sums of the form CI1, where I look at all words of length bigger than or equal to 1, CIK, and then I kind of bracket together all of these generating terms, E1 up until EID. So like EIK minus 1, EIK. Yeah, so I bracket together all of these guys in every possible combination. So the space L contains all series of this form, where the brackets are computed according to this formula here. Okay, so then the theorem here is that the logarithm of the signature is a highly non-generic element of the space of formal series. It's actually going to belong to this space L. So this is the statement of this of the theorem, and this is a priori highly kind of non-obvious, at least certainly not to me. So just by starting off with this definition of the signature using iterated integrals, it's not clear that if you take this formal logarithm inside the space of formal series, you're going to get something that can be represented in terms of Lie brackets. Okay, so in other words, for every path x, you can find coefficients for each word CI1 up until IK, such that the logarithm inside the space of formal series can be written as this big sum like this. Okay, and so now you can kind of heuristically see why this is a reduction in information, because remember that I mentioned that the signature took values in the space of group-like elements, so which was defined using the shuffle product. So the space of group-like elements was not a vector space, so its defining relations were highly nonlinear. But once I take this this logarithm, I actually end up in a linear space. So it's kind of like it's a way of projecting down to a slightly nice linear space. If you like, you can think of this as a transformation from moments to cumulants as well. So if you're statistically inclined, then maybe this also makes sense. So we like cumulants because they're perhaps a slightly more compact way of representing moments. For example, the fourth cumulant measures kind of strictly the fourth order interaction, whereas the fourth moment has like a fourth order interaction plus some of the remaining terms from the second order interactions. So this is analogous to reducing from moments to cumulants. Okay, so let's look at a concrete example of this statement. So let's consider two straight lines, two linear paths. Xt is equal to tx and yt is equal to yt for two vectors x and y. And then recall from the previous exercise that we had the signature of x was e to the x and the signature of y was e to the y. Then suppose I wanted to concatenate these two guys together. So now maybe if x was, this was x and this was y, then the path that goes first along x and then along y, this is going to be this path x concatenated with y. Then the logarithm of this new path. So first of all, we pre-process it with Chen's identity to give us this product inside the space of formal series, and then the statement of the theorem on the previous slide was that this logarithm is a formal Lie series, so it can be always represented in this way up here. So this inclusion follows from the theorem on the previous slide. Okay, and so maybe at this point, this might look a little bit familiar to some people. So there's actually another way to see this. So the fact that this is represented as a sequence, as a sum of Lie brackets, is in fact the content of the Campbell-Baker-Hausdorff formula. So perhaps people have seen this in some of their undergraduate courses. So the Campbell-Baker-Hausdorff formula so qualitatively, it's exactly what I just said. So the logarithm of e to the x times e to the y can be represented as a formal series in terms of Lie brackets. And quantitatively, you can get explicit expression for the coefficients of each Lie bracket. So it begins according to this kind of formula. So if these Lie brackets vanish, so if we were kind of in a commutative setting, then all of these terms would vanish, and we'd just be left with log of e to the x times e to the y is equal to x plus y. So this is what happens, for example, for real numbers. And this is actually what happens if d is equal to 1. So this is also if d is equal to 1, then all of these things vanish because there's no all the Lie brackets will vanish in this case too. But in general, this space of formal series is non-commutative, and so in general we need all of these brackets. Okay, so I thought this was a nice connection to kind of emphasize, and it's furthermore relevant for us because you can actually compute the log signature starting off with the Campbell-Baker-Hausdorff formula. So I know of at least one package, this II signature package, where if you wanted to compute the log signature directly, it turns out to be faster to use this Campbell-Baker-Hausdorff formula to make this computation for two piecewise linear paths directly, as opposed to first computing the signature using Chen's relation and then taking the formal logarithm. So this kind of this link between log signature and the Campbell-Baker-Hausdorff formula is not only kind of a curiosity, it actually can be made into a very concrete application for computing the log signature. In fact, so the fact that there's this Campbell-Baker-Hausdorff formula is the reason why maybe you noticed on the previous slide, I called this the generalized Campbell-Baker-Hausdorff series. And the title of Chen's paper where he first proved this was a generalized Baker-Hausdorff formula. There's a deep connection there. Okay, so I think that this is essentially everything that I wanted to cover about the signature itself. So this is the final property of the signature that I wanted to present. Now we're going to head a little bit more towards towards applications and how one might want to apply this in practice. So I'll probably even finish this part before the end of the lecture. So remember that we had a general pipeline. So let me remind you that there was this pipeline that we went from data to path.
ILya, sorry, ILya,
Yes.
then for a recap to see if I get this straight.
Yes,
So
yes.
we started from the path, and you introduced the signature, and then you showcased a few of its properties, and you made an argument that said, look, this looks pretty cool, but this still doesn't have the right manipulation properties that we're used to when we want to do maths, or then later for a later purpose. And then you introduced now the log signature, you introduced a sequence of the properties of the signature itself, and this final representation at the cost of introducing this extra Lie algebra to work with the log signature. And it's this final object that you, if I understand this correctly, that has really nice properties that we are very used to use as we manipulate functions and so on, but now with this more complex object that's called the signature. Is this, my understanding is correct?
Right. So yeah. So thanks for the question, for the recap. Actually, that was a nice summary before progressing. So yes, you're essentially correct. The only point that I might stress is that, so I presented this log signature as a way to reduce all of these redundancies that happen because of the shuffle product. So we had this, for example, we had this S of x11 was always equal to, I think, like 2 times S of x1 or something like this. So there were 2 terms of the signature that were algebraically related. Sorry, there should be a square here. They were algebraically related. And the log signature does not have these redundancies. So in general, there's no relationship like this for terms of the log signature. In practice, you don't always work with the log signature, and in fact, I personally have never worked with the log signature. It's more of a perhaps a different way of looking at the signature that is more helpful for some applications. So now you have these 2 ways of looking at these signature features. You can either look at the signature itself, or you can look at the log signature, and it depends on your application which one is better.
Okay. I ask specifically as Blanca went yesterday through these applications with the signatures, and for her very specific, for the 2 problems in machine learning that she presented, she was using the log signature. So I was wondering if it's you set up the signature as the common purpose object, but in fact, when you have to do computations, or you're doing the computations and implementations, you end up by using the log signature as it is the more practical object. I mean, the way that you've described it, encodes less information. It has all the screws tightened up so that you don't have duplicate information and things like this.
Exactly. Yeah. So it has So it has the same exact information, just in a more compact form.
Mm-hmm.
But again, I stress that it really depends on the application that you're after. So for example, if you're linked to working with linear methods, so you're only going to ever use linear regression in your life, then working with the signature is probably better than working with the log signature, because, you know, if you're working with linear methods, you're never going to square this term of the signature, and so you'll never actually like having this extra term in the signature itself is going to be very helpful for linear methods.
Thank you.
So yeah, it depends on a number of factors, basically. So now, but the point is that now in your hands you have 2 ways of looking at this information.
ILya, could I ask a question as well, please?
Yes, please do.
It's more of a comment than a question. I think it's the question is, do you think this is a good example? Because when I think about the simple example that you gave, much earlier when considering the signature was you take a linear path and then consider the signature of this thing, and what you get is sort of e to the the sort of final increment of the path. If you So if you take the log signature of this, you obtain that the first term is a constant equal to the increment, I think, and then after that you get terms that are all zero.
That's right. Yes, exactly.
Yeah.
Yeah.
And so what you can see in that is that if you get the log signature of some path and you get the first term is some constant and then all terms afterwards are zero, that is something that absolutely captures that, you know, this is a linear path. Whereas with the actual signature, you've got to check, oh, so the first term is this, and the second term is this, and the third term is this, and there's that's the redundancy within it.
Yeah, that's a good point as well. Yeah. So what William is saying is that if you look at S of x, so let me just maybe emphasize this point. So if this was a straight line, then this would be essentially 1x, x tensor 2 divided by 2 factorial, and so on and so forth, whereas log of x is equal to just x. So so the log signature captures exactly the increment of your path, whereas S of x contains all the powers of it. So this is not like, I don't want to say that this is somehow a very deep, at least not for these linear paths, that this is somehow a deep kind of, that the signature is somehow a much deeper object than the log signature. It's just like if you were, so when you think about a machine learning algorithm, you sometimes want to feed in just your vector, but sometimes you want to feed powers of the products of your vector. Again, depending on how nonlinear your algorithm is. If you want to feed in powers of your vector, then you will want to feed in the signature. But if your machine learning algorithm is already discriminative enough to and nonlinear enough to actually pick up those powers itself, you might want to feed in the log signature. So this is the difference. I see there's a hand raised.
Yeah, there's one more question.
Yes, please. Sorry, it's muted, I think. Sorry, it's still muted.
Yeah.
Maybe we can ask to unmute.
Yeah. Yeah.
Sorry, I can't hear you.
You're on. Sorry. Yeah, the Zoom. You have to unmute. Yeah. Thanks.
Yes. Please go ahead.
Do you hear us?
Yes.
Yes.
So,
yes.
Do such notions of exponentials and logarithms have a geometric meaning? You mentioned Lie algebras, and they have their own notion of exponentials.
Yeah. So so indeed, the fact that I called the place where the signature lives a group, and the place where the log signature lives a Lie algebra, indeed kind of comes from a very geometric picture. So formally, and in fact you can make this rigorous, the space of group-like elements, this is the if you apply kind of so it's a group, it's an infinite dimensional group, but it's even possible to put kind of a differential structure on it, such that when you take its when you look at its Lie algebra, it gives you precisely this space of Lie series. So yeah, so you can think of the log signature as being in some sense you can think of the space of Lie series as being the tangent vector, the tangent space at the identity of this group. And so if you think of it maybe as a chart, so if you think about, this is 1, so this is G of RD. So this is the place where the signature lives. So maybe the signature lives over here. Then the Lie algebra is a linear space. And and this is like the logarithm map. It's going to map it to, it's going to map 1 to 0, just like the usual logarithm map in a Lie group does. Then it's going to map well, it's going to map the whole group down to the Lie algebra in a diffeomorphic way. So it's a bijection. So this log is this is a bijection. And normally in Lie groups, you have to work with the neighborhood of the Lie group in order to make this actually to make this log map converge and well defined. It turns out that for this, essentially exactly using this graded structure that I described in quite a little bit of detail at the beginning of the course, this log map makes sense for the whole group. So if all of these elements get mapped down to something inside this linear space. So this is, yeah, so the intuition that you have from Lie groups and Lie algebras as being kind of like tangent spaces of the identity, this carries over to this picture. It's just like an infinite dimensional version of that. Yeah.
Thank you very much.
Thank you. Okay, yeah, so are there any other questions about this actually before we move on to the next part? Okay, so if not, maybe let me just, before wiping this out, I'll use a different color. Recall at the beginning, I gave a general pipeline, so for using the signature method. So the first step was to transform your data into a path, and then the path got transformed into the signature. And then after that, we looked at the learning algorithms. Well, I said that you have to apply learning algorithms. So before, in the first 2 lectures, we were really interested in this path to signature, and now I'm going to look at this next step, the data to path step. So how might one transform data into a path in order to apply the signature method? So this will probably be quite a short section. I will probably get onto the next one even before this lecture finishes. So consider, we're going to go back to quite a general setting actually. So consider that we have some set X. I'm going to denote it by this curly X, and it's perhaps a nonlinear set, a nonlinear space. It doesn't have to have a linear structure. So remember, it could be something like an alphabet, or it could be a set of graphs. So these were 2 examples I gave right at the very beginning. Suppose we have time series inside of this, a time series taking values in this space, denoted by little xti. So to take the signature, we first need to we need 2 steps. Step 1 is to apply some sort of a feature map. So we're going to pick some sort of a map phi, which is going to map our space X into RD. And this is going to give us now an RD value time series. So I'm going to denote this by capital X. Okay, so just a couple of examples. The simplest one is the kind of the canonical embedding, so the simplest setting. So if X is already RD, if we're already tracking, say, D assets in finance, then in principle, you don't have to do anything. You just take phi to be the identity and you get already an RD valued time series. So another one that we're going to look at a little bit further are kernel embeddings. So there's more on this soon. And just as maybe a precursor to this, something quite interesting that happens is that it's actually possible and still retain computability to replace RD by some sort of an infinite dimensional space. So this is something perhaps to look forward to. And quite an important remark is that even if we're able to identify the space X with RD, so even if we're already living in Euclidean space, our time series already takes values in Euclidean space, it's often very helpful for learning algorithms to apply some sort of a non-linear feature map phi. So just because our time series takes values in RD doesn't mean that we can't improve our learning algorithms by applying some sort of feature map first. And then the second step is that, recall that we define the signature always for continuous paths. So the second step is to somehow construct a continuous path from this time series. So there's several ways to do this. Perhaps the simplest way, which is, I guess, the most common way done in practice, is just to use piecewise linear interpolation. So if you're given a time series, so maybe according to this graph on the left, then piecewise linear interpolation now kind of connects up all the points in a straight line. Okay, and so here time is discrete, whereas here time is now becomes continuous. So yeah, there are other possibilities, like you could use something called rectilinear interpolation. So sometimes for good reason, you might want to move along axes in a particular order. So you don't necessarily always want to do a straight line interpolation. Okay, so so once we have our paths from data, we often need to pre-process those paths in some way. So we need to apply some sort of transformations, some further transformation directly to the paths. So previously I talked about transformations on the target space, on the space X. Now we actually want to apply some transformation to the resulting paths. So a couple of examples of why we might want to do this. So recall, I always emphasized that the signature is really a function on unparameterized paths. So if I reparameterize time, the signature doesn't change. And while this in some sense could be a nice feature, so for example, if you might have some data where the exact parameterization is not important, like a text, you know, I assigned the numbers 1, 2, 3, 4, 5 to the characters, but I could have also assigned the numbers 21, 22, 23, 25. It doesn't matter what those numbers were. It only matters about the order. There are other applications where the time parameterization is absolutely crucial. So, for example, you might think in finance, whether a certain operation happens 1 second after the previous operation or 10 seconds after the previous operation, this can be very, very important. And in other aspects, so maybe in certain physical applications as well, this could be extremely important. So for much data, time parameterization actually really matters. So we sometimes need to be able to encode the parameterization of time before we compute the signature. Another example, perhaps even simpler to see, is that we saw right at the beginning that for a one-dimensional path, the signature was essentially only depended on the increment of the path. The signature only encodes the difference between the endpoint and the starting point. So we had this formula. So this can also be catastrophic if you wanted to apply the signature to a one-dimensional time series. So there's plenty of one-dimensional time series that are very, very interesting and very important. And we certainly want to be able to learn something about them. So in order to do so, we need to do something to the path before we compute the signature. So we're going to describe 2 transformations, and this is a non-exhaustive list. It's just the ones that somehow easy to describe. So the first one is time augmentation. So it's essentially exactly what it sounds like. You augment the path by adding time. So if we start off with a path in d-dimensional space, then the time augmented path x bar is a path in 1 plus d dimensions. It's given by so I'm going to keep the coordinates 1 to d the same, and I'm going to add a 0th coordinate. So just to not shift the whole index over. So I'm going to add time in the 0th and the 0th coordinate. I'm going to call this x of 0. Okay, so this changes the dimension of the path, dimension of the space where the path takes values. So if we started off with a 1-dimensional time series, we end up with a 2-dimensional time series. And so now the signature is actually going to be quite non-trivial. So just as a remark here, I wanted to show something that I thought was quite neat. You can prove a very special case of tree-like equivalence in the setting, which is that, so this is perhaps a much simpler property to understand than the full tree-like equivalence. So if I give you two paths x and y, and I augment them by time, so I add time in this 0th coordinate, then the statement that their signatures are equal is well, relatively easily seen to be equivalent to the fact that their derivatives are equal. So the two paths are equal almost entirely, like including their parameterization. So this is really x of t is equal to t for all t in AB. So the only way that two signatures of time augmented paths could be equal is if the two paths are different by they differ by a translation. So this is the only way that so we only lose kind of the base point of the path by taking the signature of the time augmented path. So I actually wanted to give a proof of this because it's quite elegant. So if we look at a special term of the signature, so we look at the word which just comprises of zeros. So now our alphabet has increased by size 1. So instead of looking at the alphabet 1 to D, we now look at the alphabet 0 to D. So I can now look at words which contain zeros. So if I look at this word, and there are k zeros, so this whole thing has k terms. Then we saw, essentially it's the exact same computation that we did in one of the exercises before, that the value of the signature of this word is t minus a to the k divided by k factorial. Okay, and so now let's look at another word where I just add an I to the end of this word, and so I here now is really comes from the original alphabet, the alphabet 1 to D. Then then the signature at this new word 0 to I is given by this integral. So I've used the inductive definition of the of the signature. So I've put this in here, and I've multiplied by the derivative of xi. So here I didn't write dx, I explicitly wrote it with an x dot. Okay, so this is quite interesting, because now we see that this the signature at this specific word, it encodes essentially the kth moment. Okay, so, well, it can be written as a linear combination of the kth moments. It would be precisely the kth moment if a was 0. So it wasn't actually completely correct here, but morally speaking, it encodes the kth moment over the interval ab of this of the derivative of x. So this can be seen as kind of if ab was my measure space, then this would be the kth moment of this derivative. So in particular, because moments over compact intervals, this actually is closely related to the moment problem that I mentioned before, because moments of a function determine the function, provided the function takes values in a compact interval. This means that the full signature really encodes the whole derivative. So I'm using here that moments determine functions. So essentially, the signature determines all of these kinds of intervals. And so, in particular, if this was equal to a to the b of t minus a to the k divided by k factorial of y dot of I t dt for all k, sorry, for all k, then this implies that x dot is equal to y dot. Okay, so this is I think quite an elegant way to see that the signature of the time augmented path completely determines the path now up to translations. Okay, and then the second way to augment paths that I'm going to present are called lags. So if I start off with a path, so this is not specific to signatures, actually. Lags are quite classical in time series. So this is more of a recap for perhaps for people who have seen this. If I look at a path in d-dimensional space, I'm going to fix two parameters, so a positive epsilon and then an integer L. And I'm going to define a new path taking values in the d times 1 plus L dimensional space. And it's going to be defined by essentially taking the lags of x. So L lags of x into the past at spacing epsilon. So I'm going to define, so at every point in time t, the values of this path. So here I should say that yi of t is really an RD. So there's L plus 1 components here. So I'm implicitly using this factorization of the target space. So the ith value of this path is x to the t minus I times epsilon. So I've kind of by increasing my dimension quite a lot, I've kind of encoded the perhaps the interaction of x with its past at scale epsilon. And so, okay, so if some of these numbers might be undefined, I mean, x at some of those numbers might be undefined because I go below a, and in this case, I say my convention is that I just fix x's to be equal to xa. This happens. So starting also with discrete data, then you can do kind of like a discrete version of this. So you don't need to actually introduce epsilon if you start off with maybe a text, something like this. So you can just introduce lags by changing the index of time. Okay, yeah, then taking say, piecewise linear interpolations. Okay, so this is I think this actually concludes, yeah. So this concludes the way that we go from data to path. So I think I've covered some of the basic ways of how, if you start off with a piece of data like a time series or a text or something, then how you might build a path in some vector space, which should still capture some of the important information about this time series. Okay, so are there any questions on this part before I move on to the next part?
Yeah, I would have a quick question. Oh, sorry, maybe the question in the chat was first.
Yeah.
Okay, so okay. Yeah, let me answer the question in the chat first. So why would you want to use lags? So the lags can capture essentially the interaction of a path with its past. So so this is another way actually. So in the simplest case, if d was equal to 1, then again the signature of x doesn't tell you anything about x apart from its increment. However, if you defined y in this way, with say L is even equal to 1, so you have xt and xt minus epsilon. So you now look at this couple, which is a path in two-dimensional space. And the signature of this guy can actually tell you quite a lot. In particular, it can can approximate things like the quadratic variation of x. So so this is most easily seen in this sort of discrete setting. So it kind of yeah, it captures how x behaves, interacts with like its previous, with its past. So it can be a way of moving from one-dimensional space to higher dimensional spaces as well. Yeah.
I'll just add a little comment on this, which is on the Blanca's presentation yesterday, when she was in one of the problems that she was described, she had picked up the time series that had computed the log signatures, then computed the 3-day lag and the 20-day lag to then feed everything into the deep learning algorithm that she devised. So there it was. I mean, Miko is going to, I guess, talk more about this kind of stuff in the afternoon. We can throw him the question again.
Yeah, yes. So these are really used actually in practice. So Blanca's presentation is an excellent example.
Yeah.
Yeah, but again, I stress that this is actually classical in time series. So for example, I think autocorrelations are built from lags. Yeah, so.
Yeah. Florian, I think you have the question.
Yes,
sir, maybe
please.
you've already answered this question, but because you said you can, like, if you have data, you can interpolate your points like in different ways. Is there a way how to measure or quantify, like if I have a deformation of my path, how much the signature changed? So if I have, for example, like a smooth deformation of my like interpolation, is there a way to quantify how much the signature changes, or if kind of, yeah, like stability wise?
Yeah. So that's actually also a very good question. It might, it also rings a little bit with this question at the very beginning of what I meant by robust features. So the short answer is yes. Actually, there is a way to quantify it. I unfortunately didn't address this at all in this mini course, but let me actually perhaps now that somebody's actually asking it, I think it'll be a good idea to actually to discuss this a little bit. I'm glad that somebody asked. And no, I did not answer this before. So the basic stability. So let me take a couple of minutes to do this. The basic stability property of the signature is that you can quantify the difference between words. So if I say fix one word, I look at the difference of two signatures like this. Then if I understand your question correctly, it's basically, can I say something like this difference is going to be small if the paths are close, right? Is this kind of the property?
Yeah, something like this, or if the deformation has some kind of regularity, then yeah, but yeah, in general, it's what.
Yeah, okay, yeah. So I can even phrase this as a deformation, like x plus h somehow. Yeah. So then yeah. So this so in kind of analysis, it's important the kind of the norms that you put onto your spaces when computing these types of these quantities. So the correct norm in this case to put on your deformation is this bounded variation norm. So that I spoke about. Alternatively, you can put, so the bounded variation norm is bounded above by the Lipschitz norm up to a constant, depending on the size of A and B. So let me maybe instead of strict to less than or equals to, let me put C in here, then another C. Maybe C1, C2. And then so this kind of statement holds. So if I perturb my path X by something which is a bounded variation, my signature is not going to change very much. And if I particularly perturb it by something which is Lipschitz, which is of course also bounded. So this is, I can write this as the L infinity norm of L infinity norm of the derivative of H. And these constants, they all depend on X. So this is kind of like a locally uniformly in X. So this so somehow, because X takes values in the space of bounded variation paths as well. So for every ball inside the space of bounded variation paths, this I can choose one constant C1 for which this kind of inequality holds, provided H is not very big. Okay, so so this is the basic stability property of the signature.
Thank you.
Yeah. And it, actually, maybe I'll even emphasize a little bit more. This same thing, this does not hold for, if I replace bounded variation with the L infinity norm of H. So if you recall from the first lecture, I showed these two graphics where kind of I coupled two stochastic processes together, a Wiener process and a small perturbation of the Wiener process. And then they looked indistinguishable to us, but actually for ODEs, and actually you could do this, you could have done this for signature terms as well, there was a really big difference between them. So actually you don't have a stability property in terms of this L infinity norm, but you do for certain other choices. I see there's a question. Is there a result on sensitivity? I'm not sure what exactly sensitivity means here. I'm just not familiar with the term.
I'm guessing this means that if you change the path a little bit, will the signature change a little bit or a little lot? I guess the result that you have on your screen at the top sort of points to this already.
Yeah, I guess yeah, unfortunately I'm not sure I can say much more beyond what's change greater than something. Oh, I see what you mean. So kind of like a reverse reverse inequality. So if you perturb it by H, then the signature will definitely perturb by something else. If I understand correctly. So I think, no, that's a slightly more difficult question. Yeah. The full signature itself will be perturbed. But sort of for one individual word, you can't find such a clean statement, I believe. Yeah. So no, this is yeah, I think that would actually be quite an interesting question, but I don't have a good answer. I see somebody else raised the hand as well.
Yes, I would have a question.
Yes, please.
For what understood, the signature of the time extended path determines the path, right?
Up to translations, yes.
Yes.
Mm-hmm.
Does a result similar to this also apply for Cadillac path, where the signature is defined in terms of the Marcus signature?
Yes, that's a good point. Yes, it will be. Yeah. So if you add time to a Cadillac path and you compute the signature using the Marcus lift, that will determine the path up to translations again uniquely. Yes.
Okay. Also for also for realizations of semi-martingale. I mean, not only for bounded variation path, but
yes. So yeah. So for this, that will also be true. Although I wouldn't know of a quick way to prove it, like I did with bounded variation. The only way I could see to prove that would be to rely on this heavy machinery about tree-like equivalence. Because once you kind of add time, you're adding a monotone component to your path, and so the path never intersects itself. This is kind of what it uses. And so a path that never, kind of two paths that never intersect themselves, they can only be tree-like equivalent if they differ by translation. So this would be the thing that I would, the only way I could see to prove this. But yes, the result would still be true.
Okay, thank you very much.
Thank you. Okay. Great. So if there are no further questions, let me move on. So I actually have only 10 minutes left in this lecture. So let me move on to the final part. I might as well make some headway on here because I'm not sure that I'll be able to finish everything that I wanted to cover in the next lecture. So this is this final step in the pipeline, which is signatures to learning algorithms. So to recap, once we've transformed our data into a path, the terms of the signature, so the signature evaluated at certain words, these can be used as features in learning algorithms. So the role of the signature here is essentially a robust data compression. So I can use this robust in a vague way, but you can think of it in terms of the stability properties that I just presented on the slide before. And hopefully descriptive as well. Yeah, so this is essentially what the role of the signature is in all of this business. It's a form of data compression. So in practice, we typically use the first M levels of the signature. So you might want to restrict attention to kind of words of length between 0 and M. So that's just a remark about what actually happens in practice. And kind of emphasizing further that the role of the signature is a data compression, is that the type of learning algorithm that you use is to some extent arbitrary, or at least it's orthogonal to the actual computation of the signature. So once you've computed the signature, this gives you a finite collection or a countable collection of real numbers, from which you choose a finite number, maybe according to this truncation of taking the first M levels. And then after this, you get a vector, and now you can use whatever learning algorithm you like on this vector, provided that the learning algorithm works with vectors. So you can use linear regression, neural networks, random forests, and so on and so forth. So the kind of learning algorithm that you use is somewhat orthogonal. I'm going to focus on a special type of learning algorithm called kernel learning, where this kind of arbitrariness is not completely not completely true. So there's actually quite an interesting link between an interesting way to connect up kernel learning with signatures. So you don't just chuck in this vector into a learning algorithm in this case. At least you don't. There's a slightly maybe better way of combining the two guys. Okay, so a little recap on kernel learning. I'll see how far I get. So the basics of kernel learning is that if we're given samples of some, so I'm going to be focusing primarily on supervised learning. If we're supervised kernel learning, I should say. So I guess kernel learning methods exist for in unsupervised cases as well. So if we're given samples from some probability distribution, say, which takes values in some arbitrary set X, and we somehow select a kernel. So for us, a kernel is just a function from X times X into R. Then there's a number of kernel learning algorithms that operate entirely on the inner products with respect to this kernel between these samples X, Xi, and Xj. So this gives us a big matrix of real numbers. And you can chuck this into what is called a kernel learning algorithm. This kernel learning algorithm does not really necessarily care about what this space X is itself. So for a nice reference on learning methods, there's a book by Sholkov and Smola. So examples of this, perhaps the most famous one is a support vector machine, but also you can formulate more other methods like principal component analysis and more maybe less well-known methods like kernel perceptron, in this framework. So for us, if you know the details of the kernel learning algorithms, that's great. It can help you a lot. But for our considerations, these are going to be somehow again a bit orthogonal. So we're not going to care so much about how actual kernel learning algorithms work. We're just going to take this as a black box that operates by kind of feeding into it a bunch of samples from our space X and evaluating those samples against a kernel. And we're going to primarily focus on the case when the kernel is a symmetric positive definite function. So positive definite in this case means that for all xi, so positive definite means for all xi in our space X, and all real numbers ci, this kind of in a product ci cj times kappa of xi and xj, which is like looking at the, so if this is a big matrix, let's call it K, then this whole big sum is essentially the vector C. So if I arrange up the C in a vector, and then I hit it with C, and I take this inner product inside of R. So here I is between 1 and n. So I always look at a finite number of elements xi and the real number ci. So then positive definite means that this this quantity is always strictly positive unless C is 0, basically. So it means that essentially it means that this vector K is positive definite. Okay, so so this is the setup for kernel learning. And what I'm going to, okay, so I'm going to give a little bit of information now about how this relates to these feature maps. So this map phi that I presented before, when we want to apply a feature map to a time series in order to land in a vector space. And then I'm going to introduce a kernel on signatures. So these xi's themselves will be signatures. And I'm going to give a quick algorithm of how to compute this, which is due to Chevyrev and Oberhauser. Okay, so actually maybe I can even cover the next slide again. Okay, so and then yeah, okay. So how do kernels kind of work, and how do they relate to this feature map that I described before? So there exists a theorem of Moore and Aron-Jean, which is not a difficult theorem, but it's more conceptually interesting. So it's more of a very interesting way to think about feature maps. So if we start off with one of these symmetric positive definite functions, the theorem states is that there exists a Hilbert space of functions on our space X. The Hilbert space is called H, and we can embed our space X that we started with, perhaps a nonlinear space, into this Hilbert space by defining it to be so X gets mapped to kappa X, where kappa X is this function where we fix X and now we evaluate over all the remaining Y's in X in the big X. So this gives us a function over X, and this function is going to be an element of this Hilbert space. And the inner product on this Hilbert space is determined by this very simple formula. So the inner product of two functions of this type, kappa X and kappa Y, is given by evaluating kappa at XY. And this space X, so the space H is often called the reproducing kernel Hilbert space of kappa. Okay, and actually the proof of this theorem is not very difficult. You essentially just define first the space, say H0, which is spanned by all functions of this type, kappa X, and then you put an inner product on this space H0 by sort of imposing this equality, and then you just take its completion. So you get a normed vector space, and then you just take its completion to get a Hilbert space. You can show that this Hilbert space remains a space of functions on X. Okay, with the last minutes, let me look at the final. Let me look at some examples of this. So in the simplest case is when we start off with Euclidean space. So here X is equal to RD, and kappa X is the classical inner product on RD. So this is the dot product, or written also XT, Y, or however you like. In this case, you can actually identify the Hilbert space H with RD itself, and then kappa X you can identify with X. So I've written these as equalities, but they're kind of more isomorphisms. So in this case, the reproducing kernel Hilbert space is just the original space itself, because it already has an inner product. A slightly more interesting situation is you can take, if we take for X to be the real numbers, and we define the kernel as being e to the minus the absolute value of the difference between X and Y, then you can identify H with a Sobolev space. The Sobolev space is H1. Just to remind you, H1 of R is equal to the space of L2 functions on R, whose derivative, so I'll write it now, is also in L2. So all functions whose derivative is square integrable, and the function itself is square integrable. Then there's no real way to simplify kappa X. It's just given by the formula above. But you can actually, it's kind of it's a nice observation that you can, if you perform this procedure, you end up with the Sobolev space H1. So it's a kind of a surprising. In the definition of the Sobolev space, there's obviously no this kernel and this exponential. They don't appear at all. This is perhaps somehow a coincidence. And so you can obviously do this for RD as well if you just replace this with Euclidean distance, but you don't end up with H1 anymore. You end up with something else. Okay, so these are two examples of kernels and their reproducing kernel Hilbert spaces. And so this the point here is that this feature map that maps X to kappa X, it injects X into perhaps a very large linear space H. So this is an injection. And while it's in general, like for example, for this Laplace kernel, it's in general not possible to write down kappa X in coordinates. I mean, I can write down kappa X as a function, but kind of as in coordinates, it's quite difficult to do this. But the point is that computing inner products inside this space H is relatively, well, provided that this kappa is easy to compute, it's relatively straightforward. So we're kind of in a situation that understanding the feature map can actually be quite difficult. You can't write down kappa X in coordinates most of the time, but computing inner products inside of this linear space is actually very tractable. And luckily for us, there are quite nice learning algorithms that only ever use these inner products. So we kind of attain quite a lot of, so in general, the larger the linear space into which you embed your original space, the more descriptive your feature map should be. And here we can actually even take our kind of feature space as infinite dimensional, as for example, with this Laplace kernel, but still retain computability, at least of inner products. Okay, and so I think I'll end here since I'm already a few minutes over time. Next time I'll look at how to apply this in the setting of signatures. Thank you.